and see the empirical result at the end. So how do those approach balance for time-varying covariates? And what's the connection or the differences in their implementations? So we still use the same notation here, and the outcome is observed at the end of the study. And here we use XZ to denote the potential value for the covariates. So here's the typical assumption, sequential ignorability assumption, positivity assumption, super. I will skip this. And with those assumptions, we can have non-parametric identification either from G formula or from IPW. Here we would like to write in another form where it is written as a conditional outcome, integrate over a joint distribution of potential covariates. And that's the motivation for the balancing condition. So there are already some ways to consider covariate imbalances for the time-varying treatment effects. And here's the papers. We would like to say that there's some difference between balancing condition and current implementation. So let's start from the time-invariant case. So for the time-invariant case, they seem to be the same because in the balancing condition, they balance the population mean, and here we use the sample means to approach that. But for time-varying case, usually it's often the case that those four, when t equal to 2, for those four treatment paths, they're balanced to each other rather than a fixed target. And that's often also the case for the covariates at time 2, where the target proposed is the potential covariates. And however, this cannot be directly get from the data. So it's often the case that the treatment paths are balanced to each other, but to an unspecified target. Here, we would like to say that G formula, APW, and SPW, they approach this target like indirectly. And let's see what happens. Similar to the time-invariant case, we write the potential outcome as a general structure can be decomposed into the H function and the phi function. And we still would like to estimate the mean potential outcomes. So if we can balance H function and phi function to the target's improbability, then we can have consistent estimators. However, the target involves potential covariates, as I just mentioned. So we need a way to approach that. So this is the balancing condition involve potential covariates. And in SBW, it is balanced by projecting each covariate onto its previous covariates and balance for the residual. And the third assumption implies the balancing condition. So what happened in G formula and APW, we can see that if we write the typical estimator, if we can write them as with the implied weights, then we can still show that the weighted means converge to the targets. So in IPW, it balances all the function in probability, and in G computation formula and in APW, it balances to the targets where for the potential targets, G formula estimated by G formula, APW estimated by APW, and SPW estimated by projection. So this has the structure of the nesting doors. as for the unadjusted functional forms, it depends on how they characterize the true inverse propensity scores. So if we would like to see the balance after weighting, here's the H function at time 1. They all achieve good balance. And here's the function at time 2. There's supposed to be 2 targets. Here I just plug in the true value, and it seems they balance it well. As for the phi function, that's the robustness come in. It seems that LPW and LSPW did a slightly better job here. So let's see a short simulation study. In setting 1, here we consider time equal to 2 and 4 covariates. And in setting 1, we consider linear outcome. And setting 2, we consider nonlinear outcome having the quadratic terms unspecified. In the table, we will show the result of potential outcome of always untreated and always treated. So in setting 1, the outcome is linear, and when we check the balance, we will say that G formula achieved the best balance because it recall that table we just showed. And from the stability is that because it's minimized the L2 norm of the variance, it has the largest effective sample size. So we can kind of see that it has the smallest RMSE in this case. As for the second setting where the outcome model is misspecified, when we check the robustness coming from the phi function, here we just use the quadratic term for assessment. We can see that IPW and LSPW did a better job. And LSPW has a larger effective sample size because it minimized the variance of the weight. So it indeed have a better performance here. So in the end, we provide a unified covariate balance perspective to understand those 4 approaches. Recall the H function and the phi function. Those are the blue pill and the red pills. And for the time-varying covariates, in that unification, we found that nesting dose structure is like this, just for remembering. Okay, that's the end of my presentation. Thank you for listening.
Should we take a couple of questions?
Yeah, great.
Maybe I have just a very simple. So first of all, fascinating.
Yeah.
You really have a fantastic amount of, to me, of work in the non-time varying case. So are you planning to just have 2 different papers, or you're putting everything in one paper? Because to me, even in the non-time varying case, the fact of putting everything in together, I think it's really helpful, very valuable.
Yeah, right now they're sitting in one paper, but it depends on who's there. It's 2 papers, but I guess.
Pressure's on you, is it? Depends on what you say, guys.
Anyway, just want to say great work.
Thank you.
Good question. So you use the AIPW for there's this West bias estimator, a multiply robust estimator where that has more robust.
Yeah.
You can be inconsistent if you don't use a multiply robust estimator. I mean, the AIPW can be inconsistent, and presumably, in that case, I would assume you could get huge bias.
Yes,
okay,
exactly.
Go ahead. You seem to know that.
Yeah, exactly. So AIPW, the estimator can be easily blow up with the both extreme weights and negative weights. So we are also would like to consider more robust approach which can be written as weighted estimators. And in fact, we compare the performance with LTMLE, and it seems the LSBW, they have comparative performance. But so for some estimators, it's hard to write it as a weighted estimator. So we did not include that in the table. Yeah, so it's like all the approach we compare, those are like the classical method with the linear regression. Therefore, they may not have the best performance in their own hand. Thank you.
Maybe one more question?
Yes.
For the LSBW, you have to get these residuals by projecting the time 2 covariates and the time 1 covariates. But does that mean you need like a separate regression model for every time 2 covariate? And if those are misspecified, is there a problem with the balancing constraints?
Yeah, thank you. That's a great question. So if the H function is got misspecified, those terms get into the phi function. And in that phi function, we are implicitly using a multinomial regression to approach the inverse propensity score. So if that can converge to the true value, then we still have the robustness. Thank you for your question.
Great, amazing. Thank you for that wonderful talk. All right, so next we have Zeyang Jie. You want to come down?
Hi everyone, I'm Zeyang, a second-year stats PhD student. Today I'd like to share my work with 11 Michael and Professor Yige Li. It's about the Bayesian safe policy learning with chance constraint optimization. Especially, we will discuss the application to a military security assessment during the Vietnam War. And recently, data-based policy learning and decision-making have been increasingly utilized in our lives, like online advertising, health, and even public policy. So for example, if you are using Google or Facebook, they will probably use your personal features to decide whether send them ads or not, or send what ads to maximize click rates. And however, when such data-based policy learning is applied to settings with large consequences, a primary challenge is to characterize and control the risk of the policy learning. So, for example, in the criminal justice, you definitely don't want to someone to be hurted when adopting a new data-based policies. And that's the motivation for our work. Today, I will first introduce the basic setup for policy learning, and then describe our Bayesian safe policy learning framework. Finally, we will discuss the application to the military security assessments in the Vietnam War. Okay, let's start. Let's start from the problem setup for the Euro optimal policy learning. So suppose we want to learn policy delta, which deterministically gives a binary decision D based on a covariance X. And we use the potential outcome framework, where the potential outcome under control and treatment is denoted as Y0 and Y1. We use this CI to denote the data for the policy learning. Notice that here we assume the SUTVA and unconfoundedness assumptions for this data, but actually we do not assume the overlap assumptions here, because in a lot of practical problems, these overlap assumptions, it can be easily violated. And here we consider the policy learning, where we want to learn a delta from a pre-specified policy class pi. And in this way, the Euro optimal policy learning can usually be formalized as finding a policy delta that maximizes the value of the policy delta, which is the expectation of Y under policy delta. And the Euro way to solve this optimal policy learning problem is this two-step strategy. So firstly, we can rewrite this optimization problem using the conditional average treatment effect tau x. This is because this V delta can be decomposed into two parts. One part is the marginal expectation under control. The other part involves the actual delta and the conditional treatment effect. So we actually only need this term. And after that, people usually optimize an empirical version of this problem. So here you can use inverse probability weighting, or you can use explicit models for the conditional average treatment effect to optimize and get a policy. And in the existing work, there are a lot of people considering the safety of the policy learning. So some people considering adding a penalization into the optimization targets to kind of penalize those policies with high uncertainty. And some other people considering a more like extreme case where the conditional average treatment effect is even not identifiable because of lacking overlap. And in this case, your way is to use robust optimization, where we pre-specify a model class M and then find using robust optimization to find a policy that is optimal under the worst case scenario. And these two methods all have some limitations. For the first way, the uncertainty is completely determined by the risk is completely determined by the uncertainty on the value function, which actually cannot fully characterize the uncertainty of the policy. Because we know when you apply a policy to the population, it may have a very heterogeneous effects on different individuals. And as for the second way of work, practical problem is the robust optimization can be intractable in practice because we really want to specify a large and flexible model class. And in this way, if the policy class from the practical problem is also complicated, it can easily get intractable. And to this end, we propose a Bayesian safe policy learning framework. So the high-level idea is very simple. We just do the Bayesian inference for the conditional average treatment effects, and then we find the policy based on the posterior, where we kind of adding some extra safety constraints based on the posterior. And with this framework, we can have like more flexible characterization for the risk, where we can take into account that a policy may have different effects on different individuals. And secondly, if we are doing extrapolations, we can do extrapolations through the prior, so we don't need to deal with robust optimization, which involves both model class and policy class simultaneously. And specifically, we propose a posterior conditional risk to characterize the risk of a given policy for individuals with certain covariates. And here, we define our risk measure based on a baseline policy, delta tilde. We assume that delta tilde is completely safe and compare the behavior of the given policy delta with delta tilde on individuals with covariance X. And specifically, the mathematical definition is defined as this way. So for individuals with covariance X, the posterior conditional risk of policy delta comparing to delta tilde is defined as the posterior probability that the new policy is inferior for individuals with covariance X. And this is our definition here. Notice that this posterior probability is computed with respect to the conditional average treatment effect. So based on our definition of posterior conditional risk, we further propose a Bayesian safe policy learning method where we maximizes the posterior expected value of a policy under the constraint that the average posterior conditional risk is small. So here, this expectation is taking over the distribution of X. And this formulation allow the interpretation of this policy learning framework can be understood as if we get a policy that satisfies these constraints, then we can see the posterior probability. We can see for new individuals, like random individuals from the population, the posterior probability that the new decision rules wrongly give a wrong treatment to individuals like him or her is very small. And that gives you an interpretation for policy learning. And here we also further propose a way to empirically solve the optimization problem by converting the previous chance constraints optimization into a constraints linear programming problem. So in practice, we can use the empirical distribution to approximate the cumulative distribution of the distribution of X. So it will become an integer linear programming problem. And here I have a graph about one example of our safe policy learning framework. So here, as you can see, maybe it's too small. Those points with blue, those blue points are individuals that actually should not be treated, and those orange points are the individuals that should be treated. And here the black line is the original, like previous data collecting decision policies. So we are in a case without overlap. The data is collected with deterministic policies. And as you can see here, these 3 dashed lines shows the learned policy under different safety constraints. So for example, for the green line, it's a case with very strict safety constraints, and it's very close to the original policy, and actually it's safe. And as you increase the chance constraint or the safety constraint, the new policy becomes like far away from the original policy. And if there's no safety constraints, we can see that the learned policy actually mistreats a lot of individuals that should not be treated. Because of time, I will skip this simulation parts and directly go to the application. So the application we are considering is a harmless evaluation system for security evaluation during the Vietnam War. So basically, the process of this system is that at the beginning of each quarter, for example, September 1969, there will be a lot of questions sent to peoples in each region and collect their answers to determine these input submodel scores. So each submodel score determines one aspect of this region, like enemy military activity or enemy military presence, also other factors. And then these 19 submodel scores are aggregated to one single security score, measuring the security level of each region. This score is 1 to 5 integer value score. And then during the Vietnam War, this score is then sent to the commanders to make airstrike decisions. And researchers have found that those areas with like higher security score has significantly less air attack during these quarters. And finally, at the end of each quarter, we will have binary outcomes measuring like the development of each region, like economy or safety, those measurements. And here, the policy learning we want to do is to develop a new way to aggregate these 19 submodel scores into the output security score to improve the final outcome of each region. And specifically during the aggregation, there are two-way and three-way decision tables used to aggregate these scores. And this is one example of the two-way tables used in the aggregation. So here it's, for example, when the inputs is one, input 1 is 1, input 2 is 1, then it will output 1. So it basically describes all the outputs for given input 1 and input 2. And the aggregation is based on decision tables like this to aggregate 19 input scores finally into the one single security score. And here we consider the policy class to be the two-way and three-way decision tables to do this aggregation. And we conduct policy learning and interpret our results by the PDP, the partial dependence importance of each input. So basically, it matters how important is each input as for the final output. And here we present results of our analysis. I guess it's a little bit small, but in the left-hand side, we are using the safety outcome as the regional safety as the outcome, and these three lines shows the importance of military factors, political factors, and socio-economic factors. So this blue line is the military factor, and this yellow line is the political factor, and green line is the socio-economic factor. And this three dashed line is the original importance of these three factors in the original security evaluation system. And as we can see, it consistently upweights the importance of the socio-economical factors and lower weights military factors. And the right-hand side is another similar graph using the economical outcome. And as we can see, it's even stressed the factor of socio-economical even more comparing to using the safety outcome, using the safety development as the outcome. Yes, that's my presentation today. Thank you very much.
So, if I understood that correctly, so the policy depends on how good the initial baseline policy is. But what if that policy is really bad? And then you're saying you want that epsilon, like you want to be really conservative, but you're starting off with a really bad policy, so you're going to actually end up with a really bad policy. So there you want to be kind of really risky and say my epsilon should be large so that I move away from the bad policy. Like how should we, have you thought sort of systematically about?
Yeah, I think, that's correct. That's like the baseline policy plays a very important role in our safe policy learning framework. So in practice, like common scenarios, maybe like you already have a policy that's running in the population and it has been examined by time and we know it's safe to run this policy. So it's more like comparing like a potential new policy with like original like safe policy you already know. Yeah, I think that's the idea of like comparing it with a baseline. Yeah.
So there's this assumption that the baseline policy is actually good. So if you're in a regime where the baseline policy is probably not very good or hasn't been really evaluated. But that's really cool.
But baseline could be no policy.
Could be no policy as well.
Yeah.
So what happens if you have no policy then?
Nobody's good. Well, I guess it depends on.
So the no policy is no one's getting the stream, and then you want to say, okay,
Yeah,
well, give it to a few
treat
people. I see. Yeah. Cool.
So one question, if you already have a very good baseline policy like fair one, why do you want to learn a new one? Is it to adapt to the new data or?
I think if the baseline is already very good, let's applying this method will give you a policy that's close to the baseline because it's already very good. I think here we want to kind of separate the goodness of a policy and like the risk of applying a new policy. So sometimes maybe like the existing policy is not the best in terms of like the value, but because it's well examined by time and therefore it's safe. So
I don't think I understood a lot of that, but one question, if I had an infinite, is this all sampling variability problem? If I had an infinite sample size, would you is that unconstrained optimization? Does the initial policy matter if I have an infinite sample size?
That's a good question. Under our current framework, it's actually not like, even if, let's say, we have infinite number of observations, some policies under our framework can still be risky because we are using like accumulated conditional risk. So, for example, if you know for sure a new policy is better than the original policy on average, but it's possible that the new policy is not good for some subgroup of the population. And under our definition, because we also take this into consideration, then under our definition, it may still be risky to apply it because it's negatively influence certain subgroup of the population. So it's kind of like the fairness issue.
That's great. Thank you so much, Zeyang. All right. Next we have Jonathan Jie.
Today I'll be talking about matching. It's a project that it's a work in progress with Professor Luke Richards. So I'll assume everyone here is pretty familiar with matching. It's one of the oldest and simplest approaches for observational causal inference. And we make the usual assumptions. And in this presentation, I'll just focus on the ATT to keep everything super, super basic, super concrete. So we observe the treated potential outcomes, and we have to sort of impute their counterfactual control. Now, matching is a very simple, borderline naive approach to observational causal inference, right? As we've seen, and these days we have much more sophisticated and advanced approaches like weighting, we have balancing, we have model-assisted approaches, doubly robust stuff, etc. So why match? And the common answer for matching is that it's intuitive, but I think it's worth digging into why we say this. And I suspect that one reason is that exact matching, at least, sort of helps us humans comprehend what joint covariate balance is. So say we want to make our control dinosaurs look like our treated dinosaurs. What do? Maybe we start by thinking about trying to balance marginal means. So we want 3 red dinosaurs, 2 blue dinosaurs, things like that. But then how do we balance the joint distributions, right? Do we notice that in our treated sample, the red dinosaurs are all small, where the blue dinosaurs all have wings? It all gets a little bit nebulous, a little bit difficult to intuit, and it gets harder, especially as we add more and more covariates. On the other hand, it's always easy to look at each treated unit and just figure out if a control unit looks like it. So you see a large blue pterodactyl, you grab a large blue pterodactyl. The nice part about matching is that simply doing that process for every single treated unit automatically gives you a matched sample with good joint covariate balance. And I think this is why exact matching is feels so nice, why we can sort of build joint balance without having to think too hard. And we can see the individual level causal inferences we're making, so the resulting matched data set sort of feels much easier to work with, particularly for non-statisticians. Unfortunately, obviously, we can't do exact matching, and so lots of work has gone into building methods that circumvent needing full joint covariate balance. So we can do this with doubly robust stuff and take model-assisted averages that directly target our estimand without necessarily needing joint balance if models are good. We can also just target balance on marginal means and other moments, as is often done in practice with matching and more precisely with balancing stuff. And I'm sure I'm missing examples, but the point is that you can sort of cleverly avoid the impossible task of joint balance and still get principled causal inference. But the issue is that these approaches sort of start to move away from the original spirit of exact matching, right? This idea that if we just do decent causal inference for every single treated unit, we could just sort of take an average and end up with a good estimate that's super transparent and super easy to understand. And so in this paper, we're sort of building on a large body of literature around almost exact matching that's been growing in recent years. Our method, and so caliper synthetic matching, as I call it, it's sort of built up in 3 stages. So first, we start with basic radius matching. You pick a distance metric. Here we're using a scaled L2 or L infinity distance metric, where the given V matrix here is diagonal, so it just represents sort of the relative importances of each covariate. Then we let all units within the radius be in our donor pool. Naturally, not all treated units are going to have within caliper matches, so we may adapt the caliper to maybe include the first nearest neighbor, maybe with some additional scaling if we want to stretch a bit more. We can also shrink down calipers to get better bias properties if there are many matches within the neighborhood. The important piece here is that we should explicitly track what I'm calling, I guess, the estimand trade-off, right? With tighter calipers, you get better estimates, but you drop unmatched treated units, right? So that changes the estimand. And then sort of as calipers get wider, the estimand approaches the full ATT that you're interested in, but your estimates are potentially worse. And so recording all calipers used for each unit allows us to visualize this estimand trade-off, which is helpful for diagnostics. And then once we have matches for each treated unit, we just run synthetic controls within each caliper. Synthetic controls, all they're doing is they're sort of projecting the treated unit's covariate onto the convex hull of the within caliper control units, right? And then it's sort of linearly interpolating the control unit's outcomes to that projected point to use that as a counterfactual. And the nice part about doing this within calipers is because it sort of gives each treated unit an explicit counterfactual control that you can look at, and B, we're sort of less exposed to interpolation bias, right? Because we're only linearly interpolating across relatively small distances within calipers. Okay, so that's the method. Now I'll quickly touch on a couple of standard properties for these types of procedures. And so many of the properties I'll be talking about sort of naturally fall out from the fact that radius matching without adaptive calipers, we'll ignore the adaptive calipers for this piece, sort of belongs to the monotonic imbalance bounding class of matching methods. And the formal definition of MIB methods is somewhat strangely technical, but the idea is just that if you independently caliper imbalance in each covariate, you get good properties, right? So for example, you can make sure that your matched units' ages are within 3 years of each other and their heights are within 3 inches of each other. And importantly, adjusting one of these calipers is not going to affect balance in the other calipers. And so here, the nice part about using a scale distance metric caliper is that any given sort of covariate-wise caliper you might want to use naturally implies a scale for the distance metric. So here we just pick the scale such that the bounding the distance metric by 1 satisfies the assigned covariate-wise caliper. So we'll just think about the distance between units, which is now just a number, rather than each of their p covariate-wise distance. And so once you have control over individual match quality, you have control over overall match quality, right? So for example, in 4.2 up there, if the individual units are close to each other, the marginal means of the treated and control samples naturally have to be close to each other, right? But more generally, again, going back to this like spirit of exact matching, doing radius matching gives you good joint covariate balance, right? Not just marginal balance. And we've chosen to characterize that here with a Q Wasserstein distance between the empirical CDFs of the treated and matched control units covariates. The intuition is pretty natural, right? So Wasserstein distance, your sort of earth mover's distance, total amount of probability mass you have to sort of move to transform one distribution into another. And because the calipers for each treated unit sort of bound how far the matched control unit's mass might have to be moved in terms of distance, the calipers for all the treated units together sort of bound the total amount of mass that has to be moved. And so, this just characterizes the joint covariate balance nature. And then once your joint covariate balance is bounded, the difference in sort of smooth functions of those covariates naturally has to be bounded as well. And so here we just note that if the conditional expectation function is nice and smooth and you're using a distance metric caliper, the expected bias is nicely bounded. This result, it looks a little fancy, but it's nothing more than sort of a simple extension of the covariate balance, right? Basically, if your x's are close, your y's have to be close as well. If your conditional expectation function is sort of nice and slopey, as the Lifshitz assumption gives. And obviously, we don't know lambda, sort of the maximum wiggliness of this function. So this doesn't give us practical bounds, but it's a nice result. And it shows how radius matching, coarse exact matching, things like that are somehow conservative in a sense, right? So using only the nearby units to impute outcomes means that in the worst case, we'll just be wrong by a factor of sort of the largest distance we've interpolated or extrapolated across. This doesn't mean that we'll be right, but at least means that we're sort of controllably wrong, which is really nice to have in observation. And this is just a final note that you can sort of then reduce down a bit more residual bias by using synthetic controls, right? Specifically, the local linear interpolation naturally gets rid of the linear bias term in the previous slide. So again, the nice part of synthetic controls within calipers is that we're a bit less worried about the conditional expectation function being super wiggly within the caliper. So just getting rid of the linear bias should hopefully get rid of most of the bias that remains. Okay, so as I said before, most of the properties I just mentioned just sort of follow immediately from the fact that radius matching is MIB. And the most famous MIB method is coarse and exact matching. For those who aren't familiar, coarse and exact matching is this super elegant matching method that just simply coarsens numeric covariates and then exactly matches them. So maybe, age gets binned as like 0 to 10 years, 11 to 20 years, et cetera, and then you just exact match on those bins. In this example, I've drawn out the gridded calipers implied by coarsening of 2 covariates, x1 and x2. So all the units within each sort of cell get matched to each other. I'll highlight treated unit T1, the triangle, red triangle in the middle. We see that it gets matched to C2, but not to C1 because C1 is sort of right on the other side of that coarsening. On the other hand, if we center the L infinity caliper here, because it's a sort of squarish caliper, and we make sure that caliper is of the exact same size as all these grids, if we center it on T1, we can make sure to capture all units close to it, right? So now C1's there, but not C2. And generally speaking, for the same caliper size, centering the calipers on the treated units kind of increases or improves your bounds on covariate balance and bias, et cetera, by a factor of 2 relative to the bounds from CEM. So it's worth doing as long as the additional computation isn't a problem. Cool. So Now let's see some of these things in action. We're still in the process of looking for a data set, but just to illustrate ideas, I'll use the LAND, our most beloved and most hated observational data set about the effect of a job training program. And so obviously, this data set comes with its, caveats. Our goal here is just sort of to illustrate possible uses of our diagnostic tools in a toy example. We're not going to add anything to this discussion. Oops. Okay, so I'll cut to the chase. Here I just make matches using an L-affinity metric with an adaptive sort of half standard deviation calipers. So two units get matched if they're within a half a standard deviation and all continuous covariates. Units with many matches only use their 5 nearest neighbors, and units with no matches get 1 nearest neighbor. And so here we're looking at the synthetic controls associated with each treated unit. And so we see that, the nice part about synthetic controls here is that it's pretty straightforward to just evaluate the quality of each individual match, right? We see that treated units 1 and 2, those matches, those look pretty good. Unit number 185, that's pretty bad. We've extrapolated quite a bit using the nearest neighbor. And if we need to summarize sort of match quality with a single number, if we don't want to be looking at all these numbers ourselves, we can also just check the scaled distance between each treated unit and its synthetic control. Maybe plot some sort of density plot. And so here, the x-axis is just sort of density plot between the treated unit and its matched synthetic control. And the vertical dotted line is the caliper that we used. And so we see that maybe a little more than half of the treated units have pretty high quality matches. But then a bunch of them don't. And so we should therefore, be a little bit careful if we want to really target the ATT, right? Since some of the treated units really just don't have good match controls. We can also make love plots, as I'm sure you've all seen before, to diagnose covariate balance. And specifically, we can sort of see what happens to balance as we allow the caliper to expand. And so here the y-axis is balance between treated and control, the matched samples. And the x-axis is the largest adaptive caliper size that is used for that amount of balance. And so as we allow more and more potential imbalance by increasing the caliper, we're dropping fewer points, but as we see, generally making covariate balance potentially worse. And you can make these plots and we can use them to sort of adjust the caliper needed and sort of diagnose potential problems with our matched units, right? So for example, we pretty clearly see here that using poorer and poorer matches tends to make the control sample older, that line's going down, and less educated. And so we should keep that in mind when we're thinking about the results of whatever procedure we take. And then finally, we can just do the same thing with the estimate to directly visualize this so-called estimate-estimand trade-off. Again, x-axis is sort of adding treated units by adapting the caliper. Y-axis is now our ATT estimate. We see that we're being as principled as possible and only targeting the well-matched units. Our ATT hovers pretty low, it's around 500. But as we add worse and worse matches, it goes up. And so this sort of gets at some of the challenges with the Lalande data set. You've had sort of experimental estimates, 800 or 1800, depending on sort of the sample used. And observational approaches often aren't agreeing with each other. And with this plot, we sort of see that we should be quite worried about the potential bias induced by some of these less matchable units, right? Our most principal estimate is relatively small, but sort of adding older and more educated controls makes our ATT estimate go way up. So we should really go back to the data and sort of see what's going on before proceeding. And that's my talk. I spoke a little bit about caliper synthetic matching. I talked a little bit about the spirit of exact matching that we're trying to go back to, and we looked at some of the diagnostics. Thank you.
Should we take a couple of questions?
I had a question on the covariate balance as you're kind of varying the calipers, because I was curious why some of the income variables, would you expect it to be worse, or why is it kind of varying more than I thought it would in terms of increasing caliper size and getting better balance in some cases?
Yeah, the yellow line you mean?
Yeah.
Yeah, I don't know. I mean, so these are L-infinity calipers, so you're sort of constrained by your worst balanced match. And so as you're stretching them, maybe you're allowing your worst matches in other covariates. And so just by random chance, the income 74 is getting better. In general, we sort of just expect there's more potential for bad balance as you get wider, not that, it'll actually be worse.
What's the difference between the synthetic control caliper matching and kernel matching? Are those related?
Could you elaborate on kernel matching?
My understanding is that for each treated unit, you you interpolate from its surrounding units using a kernel. I don't really know too much about that, but is that? Seems like that's.
Yeah, I suspect they're related. We have a lot of experts here to answer better, but synthetic controls is usually formulated as this explicit optimization to find these weights to project appropriately. Kernel weighting is usually formulated as like, I have this kernel and these are the weights. And in terms of connections between them, they feel similar, but in terms of formal connections, I'm not aware how that works.
Thank you.
So how do you pick the caliper? That's what I always wonder in these types of things where you have a hyperparameter.
Yeah,
you have that really nice plot, but that just tells me
It changes.
things completely change depending what I pick.
Yeah.
So, have you thought about trying to be systematic about, just sort of practical recommendations around this?
Yeah, that's a very, very good question. I haven't been able to come up with anything super clean. So there's sort of two aspects to this. One is picking the distance metric, right? And so here we sort of take the coarse and exact matching view of just have someone pick it. You can also go ahead and optimize it as a lot of people have done using a holdout set or things like that. But then given the distance metric, you're kind of stuck with the data that you have when you're picking the caliper. So it's okay, if I look at this subset of units for my most principled caliper and I look at them and they look okay, then maybe I just use that. If it's obvious that there's certain trends in the covariates, maybe as we go out, everyone gets older and less educated, and I don't care about that subset or things like that, then I feel happier widening. But mostly, the idea here is just to be sort of at least transparent about where these estimates are coming from, instead of just spitting out something at one of the ends.
Great. Awesome. Great work, Jonathan. Thank you. So quick 5-minute break and we'll start at 20 past, okay? Oh, someone left their phone.
But it was randomized, right? It's randomized. Right? So that means that by the randomization works, they should be very.
Okay. Wait, you wrote all the vignettes. Okay, I've done a lot, with those. Okay, it's awesome.
Yeah. Fairness concept. There is information share is not that large.
Okay.
And the use of API.
Okay. Yeah. What's your best content? Okay.
Submit a request.
Yeah.
I've been writing our package. So in that case, they should actually have
Yeah.
Thanks so much. Some of this stuff also
That's true. My thought was that, at least in this case, I would assume that they would have been you're right, actually, I remember this kind of wrong. I would assume they would have sort of this is not practically what they can do in practice, they don't have it, but they can sort of see how, if the caliber changes, how they're, not just how the analogy is, but actually how the ATT diverges with the true empirical. Right, but I guess the point is that the medical data, they know they have there's an experimental estimate of the true thing. So they could then sort of broaden the caliber out and sort of see how sort of the risk of the estimate, which I assume they would have done, but
Thank you so much.
I want to show you.
change the caliber, how the ATT changed. You can show how what I care about is the relativity.
Good to see you.
Oh, was like a Dae Woong Ham at the bottom or something? I didn't remember seeing it. This is overlooked. I don't know what you think. I don't think. Yeah.
If you're interested,
Awesome. Take a photo.
yeah, and and we can tweak we use here the
This is great.
I have any combination of all of that.
Okay, awesome. Thank you so much.
Right, well, that's like, what I'm thinking about all the time. I've encountered this residual balancing.
You can imagine there's just so many.
Well, that's just always kind
Yeah, I'm excited for your session.
Thank you.
Good.
Yeah.
Where's that?
Welcome to Stratomax.
No, I didn't know. I'm gonna probably go we usually just try to like the family's coming to visit us though. We're doing a little bit of renovation at home, so they'll be here visiting us.
So I really had my.
Wow, that's really cool. I love your
Yeah, I'm trying to graduate.
Oh, wow.
It's a lot.
She made you work. Made you work on the break.
It's made it fun. It's very fancy.
Like New Year's resolution.
Yeah, exactly.
Exactly. Everyone just wants to be there.
So you did
Oh, that's so sweet.
Yeah, grab us. Let's ask you a question.
Yeah,
Okay, he's a postdoc kid across the river, like biostats or something. Good guy. Does lots of Causal for stuff.
Yeah.
I mean,
All right, let's start it. All right, so we've got two more talks. So I'm super excited. Ellen, you want to take it away?
Yeah, thanks. Okay, so I'm Ellen Considine. I'm a third year in biostatistics advised by Francesca and Rachel Nethery. And for this project, I've been collaborating with a postdoc in our group, Mauricio Tech. So a bit of introduction to the problem setting that we're in. We have US county level data from 2006 to 2016 in the summer months. We have heat alerts, kind of data, just binary treatment from the National Weather Service, and we have health outcome data from Medicare, which is people greater than the age of 65. And then we kind of have this system, a very rough jag, but thinking about, okay, weather and whether we send a heat alert and then the health outcomes all interact with themselves and then everything kind of interacts with each other. A bit of background on kind of past work looking at heat alerts and health, both actually from our group. The first was a study using kind of what we think of as traditional epidemiological methods to estimate the causal effects of heat alerts on hospitalizations and mortality in the Medicare population. And then the second paper was looking at using stochastic interventions to look at if we change the probability of issuing a heat alert, how might that affect hospitalizations and mortality. And then for this project, what we're thinking about is, can we basically kind of develop a sequential policy for each day deciding whether or not to send a heat alert based on what we've already done. So this is similar to the policy learning that we heard about earlier in Zeyang's talk, but it's taking into account the sequential dependency in what we're doing. So actually, quick show of hands, who here is somewhat familiar with reinforcement learning methods? Okay, a little bit. just wanted to make sure I'm not telling you what you already know. So a brief intro or review for those of you who are familiar is that in RL, we're thinking about an algorithmic agent using and optimizing a policy, so in our case, when to issue a heat alert, to interact with a system to maximize its reward or minimize its penalty, so in this case, trying to minimize deaths or hospitalizations. And traditional reinforcement learning that you hear about, an AI learning to play chess, drive a car, most often happens in what they call an online setting, which I like to think of as kind of a controlled experiment, where you're able to interact with the system to get more data to test out your hypotheses about what might work. Here, we're in what's called an offline or batch setting, which is then similar to an observational study where we have a set data set, and the goal is to try and learn an optimal policy based on this sampled data, ideally to improve on the policy that generated the samples, which we call the behavior. So now switching to what types of methods do we actually use for this. So our general reinforcement learning approach kind of builds off of something called a Markov decision process, which appears in many other places in statistics. But basically, that's describing the sequential trajectory of what's happening. So I'm at a state S, I take an action A, in this case, whether or not to intervene with a heat alert. We receive the reward, which is the health outcome, and then we move on to the next state S, prime. So there's this whole huge family of RL methods called Q-learning, and that's actually both, Q-learning exists in both an online and offline space, but we're talking about offline Q-learning. And that's basically to develop a model for the expected return or future cumulative reward from taking action at the place that I am now. And we calculate this using recursion across all of the time points in our episode. So in this case, days in each county summer. And then we actually have to evaluate whether or not the policy that we are learning or trying to optimize is doing any better than what happened before. So this requires estimating the counterfactual reward under the new policy. And when this becomes really tricky is when we have to account for this sequential dependency, so these counterfactual trajectories. And this is really where the causal inference piece comes in. So for the rest of this talk, I'm kind of going to lay out some major challenges that we've encountered. So my background in research is more from the environmental health setting. And then, I was interested in kind of learning about the sequential decision-making policy optimization. So trying to learn, can we take these RL methods that have kind of met so much success in lots of other settings, video game, playing self-driving cars, can we apply those to this environmental health setting where we have these kind of more messy observational data sets, and in kind of the epidemiological space, we often have to do various, causal inference tricks, et cetera, to be able to identify relatively small effect sizes, because in environmental health, there are tons of other things that are happening in a system, right? Traditionally, when we're thinking about air pollution or heat, the variation in those environmental exposures is only accounting for a relatively small proportion in the changes in health outcomes compared to something like socioeconomic status or age, those types of things. So what are some of these major challenges that we've been encountering and kind of coming up with at least ad hoc solutions for now? The first one, I'll be kind of sharing both RL terms and then the statistical terms. In RL world, they call it distribution shift. In statistics and causal inference, we typically talk about lack of overlap. Statistical confounding, of course, relatively small reward signals or effect sizes, as I mentioned. This issue of spatiotemporal non-stationarity, so does, a policy that works in one county in 2006 necessarily to apply to a different county in 2008? Numerical instability comes up a lot in especially these RL settings. And then the question of uncertainty quantification. As statisticians, we always want a confidence interval out of there. And that is, again, trickier when we're accounting for sequential dependence. In this talk, I'll be focusing on the first three as kind of most relevant, I think, to the people in the room. So distribution shift, lack of overlap. This figure in the top row is showing what might happen if we just let an RL agent kind of issue alerts whenever it wanted to. And the x-axis is a little small, but it's just the day of summer. So we might imagine that the RL agent just issues a bunch of alerts right at the beginning of the summer, compared to the behavior policy, which is issuing the most alerts in the peak of summer in the middle of it. And that makes it really hard to do off-policy evaluation because we're trying to kind of estimate the health outcomes on this unseen action space. Whereas if we try and constrain when the RL agent is able to issue an alert, we might be able to get kind of more overlap and actually be able to kind of see whether we're doing any better. So the solutions that we've taken so far are first to restrict the number of heat alerts per county summer to that was actually observed. So in a county where there were 10 alerts issued over the course of a summer, the RL agent isn't allowed to issue more than 10. And that's kind of helping with this, covariant balance issue, because if, an RL agent, if we were trying to think of letting it issue as many alerts as it, wanted to, it might issue them every day, and then we wouldn't be able to tell what was going on effect-wise. And then our second, do you want
to say this is similar when you get too many mails from the dean's office.
Oh, yeah, no, exactly. In the kind of like mobile health space where they're interested in using these RL methods, they refer to that as alert fatigue.
Yeah.
So very much so.
So yeah, you described it much more professional, but I think.
Okay. So then our second approach for this problem, which I actually think is much more generalizable, is restricting the alerts to days when the behavior probability by the National Weather Service, whether that could have reasonably issued an alert. And so this is basically just a propensity score, and it's saying we don't want that to be 0, and that helps generate the figures that you see then in the bottom row of kind of bringing these two distributions together. Also, just to give a brief sense that we're not kind of overly constraining the RL agent. So this plot is just showing the allowed alerts under this kind of like probability threshold constraint. So the x-axis is how many alerts each county summer actually sent. And then this on the y-axis is how many kind of days that county summer then has under our kind of constraint. And the key thing being that these are all greater than the number that they would have issued in the first place. And then the other thing I guess I'll note here is the colors of the points correspond to the zone in the US that kind of describes the climate, and it's just clear that the zones are issuing very different numbers of alerts. So then I wanted to mention the issue of confounding. So typically in RL settings, in most online and offline scenarios, you're not really thinking about kind of confounding in the rewards as much. A challenge that we encountered when we started working with this data set is that some hospitalizations that are obviously related to extreme heat, so heat stroke or dehydration, actually increase when heat alerts are issued. And the study that identified this hypothesized that it was because people see a heat alert and then are kind of more alert for whether they or a relative are experiencing symptoms that might obviously be related to heat. However, this frustrates reinforcement learning attempts where heat alerts are our main intervention to try and decrease these hospitalizations. So the approach that we're taking here is just only to consider hospitalizations that are not obviously heat related, but have still been shown to increase with extreme heat in the Medicare population. And the last kind of major challenge that I want to mention is this one of small reward signals or effect sizes. So only about 2 or 3% of variation in deaths and 6 to 9% of variation in the heat-related hospitalizations in our data set are actually explained by our feature space, and we've added quite a number to kind of get at different parts of the system. But then this again is kind of expected in environmental health settings. And the issue then is that the reinforcement learning model has a lot of difficulty distinguishing the signal from the noise. And so the kind of direction we've ended up going now is to kind of have a preliminary model for the health outcomes and then use these estimates in both the Q-learning and the off-policy evaluation. And the idea is to kind of help identify the effect before we even think about the sequential policy optimization piece, which seems obvious in retrospect, but most reinforcement learning, you don't have to worry about it because the effect estimation and the policy optimization are usually happening at the same time. So this is really more kind of where the causal inference piece comes in. We're currently using some domain knowledge in the model structure. For those of you familiar, it's not anything especially sophisticated now, kind of just an augmented T-learner. And then briefly, I'll just give an overview of some of the other challenges and solutions that we're thinking about in this setting. So for spatiotemporal non-stationarity, we've just been trying to think about a lot of important spatial or temporal features to help the Q-learning model find a more nuanced policy. We've had to be kind of experimenting with a lot of RL deep learning tricks to get the Q-learning to converge because it is just very numerically unstable, and that's kind of common in that setting. And then for the uncertainty quantification piece, we're planning to use a combination of MC dropout, which is a way of sampling a distribution from a neural network that has kind of proven properties, and then kind of the idea of like Bayesian propagation of uncertainty using samples. A couple additional considerations. So as I've been going through this project, I've kind of been thinking to myself, is there real potential for these methods to become frequently used in environmental public health settings or similar policy settings? And one of the main considerations that I thought about is this balance between kind of the nuance of the policy versus the usability by organizations such as the National Weather Service, and especially, at least in the ML space, I'm starting to hear more about, like human in the loop decision-making systems, and that whole question is something that I think there's a lot of room for development for, especially kind of these settings where we're used to not even thinking about the possibility of an AI kind of helping in that decision. And then the other thing that I've encountered myself, but I suspect for a lot of others too, is just kind of a high barrier of entry to this sequential decision-making policy optimization space. So either we need individuals who are kind of familiar with the domain knowledge, environmental health, sequential decision-making, causal inference, deep learning, computational tools, or we need kind of more collaboration across these fields to come up with like usable solutions to these types of problems. With that, I will close and thank the National Studies on Air Pollution and Health Group, who have a lot of representation here, and also NSF for funding.
Cool. Let's take some questions.
Sure. Arpita, I think.
Yeah, so quick question, what algorithm are you using? Like when you say Q-learning, are you just using Q-learning or like something fancy like DDPG?
Kind of modified just DQN at this point. We've been experimenting or starting to think about moving out to some of the other like CQL, IQL just for also comparison, but really figuring out the kind of first effect identification was a critical piece that we were kind of focusing on up to this point before experimenting more with the Q-learning.
Yeah, you can actually use like deep deterministic policy gradient methods, which is also deep networks. But I think you mentioned that there's like the computational problem that you're facing because of the large data and training, right? So that'll kind of become easier if you're using policy gradient.
Yeah, I think so. The kind of issues with the DQN that we've encountered have less to do maybe with the size of the data and more just the tuning parameters being really finicky.
And like, it's not converging, right? So yeah, policy gradients kind of help.
Okay. Yeah, we should maybe talk about that with Mauricio. Thanks. Yeah.
How are the he/hers decisions are made currently?
Yeah, that's a good question. So basically, the National Weather Service has some kind of like broad recommendations, and then there are also more regional or local either policies or just officials will kind of use some of their personal discretion. So there's a combination of like thresholds, say in the north, if it's like above, if the heat index is above like 105, they are kind of likely to issue an alert, but there's also this piece of human discretion.
Do you think there's the option to intervene? Like after you build this and you come up with a new policy, do you think there's the option that, parts of this will adopt it and then you could sort of sequentially keep improving that?
That's a good question. So that I think would be like a really cool outcome of this. Our collaborators at Boston University are like in touch with National Weather Service. So in the past, when they, for instance, did the analysis seeing that increasing the probability of issuing heat alerts could be health protective, a part of the National Weather Service decided, okay, we'll just start issuing some more alerts and see what happens. So I think that would be a very cool outcome, TBD whether that's possible. Oh, yeah, sure.
Thanks, Ellen. This is really interesting. I just was interested about the approach you did for confounding, which I think was really clever. But I was curious about the impact of kind of not focusing on kind of aspects that you would have expected to go up, and how that impacts that lower effect size estimate. Does that make it, if you are not going to look at, because is that bias in kind of hospitalizations that are directly you would expect to be related to heat alerts?
Oh, so you're saying, for instance, wouldn't we expect that the effect of extreme heat be actually extra strong for something like heat stroke, but those are exactly the hospitalizations that are confounded?
Yeah.
Yeah, that's a really good point. Honestly, I don't know. So yeah, in a way you're saying the effect that we're observing, not considering those hospitalizations, is smaller. Yes,
That'd be the case. Yeah.
but at least what we've been seeing so far is including those in the DQN just really confuses things. And when I have run a pooled estimate for all of the hospitalizations together, you're basically just not able to identify the effect of an alert. So it's possible if you looked at each one individually, you could find something, but so far we haven't had success there.
No.
My question was very similar to that, actually. I'm wondering if using this kind of more relevant but confounded outcome would give you something like an intent to treat effect, where it actually is the effect on hospitalizations, but that effect has two pathways: one through people becoming more aware of their sensation of being hot, but one also in them taking action to reduce those. So although they may cancel out, and that's why you're failing to find an effect, maybe is it possible that actually is the effect of a heat alert?
I mean, for those types of hospitalizations.
Right.
Yeah, but I guess the thinking it would be, I mean, yeah, for those hospitalizations we do care. I think for this project so far, it's been, can we identify an improved policy over what the NWS is currently doing for at least some of the hospitalizations. So for now, we're trying to see if we can find anything different. But yeah, to your point, if we don't see an effect for those hospitalizations, the current policy might be fine.
Okay, thank you.
Oh, I don't know if we're out of time.
I think we're out of time. Okay. Maybe we can take those questions offline.
Yeah, sure. Yeah.
Very well, Kevin. Thank you so much. And last but not least, we've got David. Yeah, my favorite is Martin's picture. Just looks like he's so deeply thinking. He's the guy on the right.
Alright. Hi everyone, I'm super excited to talk about my work. It's actually in collaboration with Netflix here. My collaborators Michael and Martin. Of course, y'all right here with their hands and photos. So just because I knew that my talk would be the last talk, I kind of wanted to start off with something we can all relate to. So if you're like me, you're on your phone sometimes, let's say at night, and you're looking at your phone, you're looking at your favorite apps like YouTube and Netflix. Then you're a couple of hours pass, you just disappear, and then you ask yourself, how they get so good, right? Because if you're like me and you're on the weekends, I stay there for hours. And
so that's why you don't work?
He's telling a lot about himself right now. He's like, I'm just on YouTube and Netflix all day.
All right. So we're doing something wrong.
Hopefully the answer is relatively self-explanatory from the title. It's really a big part of it is experiments. They really learned everything they can about you. And just to give an example from Netflix, look at how it kind of looked like in 2008. Back in the DVD days, kind of looked like that. But now what it looks like is, a little bit fancier, a little bit more slick. And the key is that every single thing that you see there, really every single thing, the size of the photo, how much, space they want that, that board to take up, has all been experimented and the winners of some A/B testing. So that is kind of how they get us so good. So having said that, I think we kind of all knew that experiments are important. I kind of want to also emphasize that it's not just doing experimentation, but also analyzing experiments efficiently. So just to motivate that, let's just think about how we think of traditional experiments. So back in the 1900s, maybe we would think about just grouping up a bunch of people in the classroom, and then you just assign half of them treatment, half of them to control, and you get their response simultaneously at the very end. But that's actually kind of not what's been happening right now, especially in large digital firms. And much like the presentation that was actually happening before me, observations arrive sequentially, and at any point in time, you can actually have sequential sort of like partial information available to you. So in this case, you can think of individuals arriving to a website, and like at time 4, you have 4 data points, and then you might ask yourself, could we like peek and do some sort of testing as data arrives? Currently, of course, the analyst traditionally performs one test at the end of some fixed time, like 1 week later. They kind of respected the design of the left, and they just do sort of one like analysis, like a t-test, and say the treatment is effective. Now, there are some issues with this, and particularly, we don't actually know how to choose the end of fixed time. It's often arbitrary, purely convenience, like 1 week later or 2 weeks later. You can do power calculations, but we kind of know that it requires specifying the alternative hypothesis exactly. It's something that's actually pretty hard. And lastly, from a purely business perspective, there's a huge argument for risk mitigation, where, for example, if you're like Netflix, you're experimenting on your customers. And experiments, by the nature of experiments, you don't know that it's actually good or bad. That's why you're experimenting on it. A lot of the times, they're negative. So you're actually harming your customers for, let's say, like 2 weeks, when you could have figured out that it was negative by the first day, for example, because their sample sizes are pretty big. So all of this kind of hints at we want to do something with the data as they're arriving, instead of just analyzing at the very end. The solution, sort of the mathematical solution to this, are confidence sequences. They've been proposed before, and the idea is that you can see that this. You can see this every time here inside the probability statement is very important. So it sort of uniformly controls type 1 error sort of like at any point in time. So you can actually check like at day 1, day 2, day 3, day 4, you will incur no greater than type 1 error alpha. So this is sort of how we would actually formalize this. So this has been around for a while. Our main contribution is that we're going to bring the design-based sort of causal inference literature into building confidence sequences. This allows for a tremendous amount of possibilities to make the settings more general, because we sort of condition on the potential outcomes. So it's non-parametric, it's assumption light, and it has sort of no technical assumptions. There's also the nice causal interpretation. We've clearly defined sort of exactly what we are estimating. And on top of that, we can extend into like panel structure settings and time series, which are much more complex. So despite having set those complicated scenarios, I just want to focus on the most simple thing for today's talk. Just the typical, you want to get the average treatment effect of n individuals arriving, let's say, to your website. They're all independent. The data is kind of nice. So this here is our quantity of interest. Just the simple IPW estimators are what we're going to be using. I don't think I have to explain too much of this. The only notation you need to know is that the W is going to be our treatment and the Y is our response. And here I made the probabilities marginal because I assume they're independent, but of course in our paper we can actually make this adaptive, history dependent, to extend to settings like multi-arm randomness and such.
What is, sorry,
That's okay.
just a clarifying question. What is an example of the treatment? Just want to wrap my head around that.
Like an example of an estimate we would care about?
No, what is an example of W in this in the Netflix context?
Oh, sure, yeah. So for example, let's say, they want to test a new sign-up page, right?
Okay.
So then they will show version A, which is the original sign-up page, and then they will show a version B, they tweaked it a little bit probably, and see if that version B generates more revenue and such.
Okay,
yeah.
thank you.
So I talked a lot about making assumption free. I'm going to be transparent about it. The only 2 assumptions we basically need is that 1, we need the probabilities to be bounded away from 0 to 1. This is completely in control of the experimenter. They can choose whether or not, of course, to assign with 50% or higher or lower. The second assumption is that the realized potential outcome is less than some potentially arbitrarily large constant m. This is again pretty mild because even if you're generating from some unbounded, infinite support distribution like a normal distribution, you can run that forever. You're never going to get infinity, and hence, every single realized potential outcome of all individuals are bounded. Right away from these 2 assumptions, I can state the very first confidence sequence for the average treatment effect. It's not super important to try to go through all of the math here. I just want to highlight a few things. So 1, it's centered around our unbiased estimator right here. It's good. There are some unfavorable characteristics of this exact confidence sequence, namely that it depends on little m here, which is dependent on big M. So that is no good because unless you're in a special case like the binary outcome case, which is actually pretty common. But if you're like in a more continuous outcome space, you may not know what big M is. And even if you do, it kind of scales with that. The second term here is the main term because the first term here kind of disappears asymptotically, but the second term here is the variance. It doesn't really have the order that we want. As you can see, the Sn here is of order n, and of course, if you're dividing an order n by an n, you're not actually going to shrink to 0. So that is obviously something we may not like, but this is actually still pretty useful in practice if you have like binary outcomes and such. Great. So one solution to this is to go to asymptotic land, and asymptotic land in confidence intervals are pretty well established. In confidence sequences is actually relatively new. Luckily, collaborators here, not collaborators, colleagues, I guess, in CMU have already worked on the asymptotic regime, and they've already formally defined what that means. For this presentation, we can just think of it informally as confidence sequences that are just valid after sufficient large time. So just to give some intuition, this exact confidence sequence here you can already see why asymptotics can help. This first part here kind of disappears asymptotically, and hopefully we can also imagine that asymptotic theory can fix the order that is more favorable. And just like that, with similar assumptions, this is basically the asymptotic confidence sequence. You can see it's centered around the same center, and the order here is basically sort of square root of Sn over n without ignoring the log terms. But this is basically kind of like the t-test, square root of Sn over n. And more importantly, there's no dependency on those hyperparameters like m. This eta parameter can be arbitrary constants that are just greater than 0. You can choose anything. In our paper, we give a practical recommendation and also a closed form solution to that. So in terms of results, kind of just wanted to keep it simple and just say that. I do want to mention the extension. So basically this confidence sequence you see here can easily just directly extend and to account for more complicated scenarios like time series and panel data where you have like adaptive treatment assignments. You can have carryover effects where like the SUPA is not necessarily satisfied, and panel data where it's even worse. You not only have one time series, but you sort of have like n time series over time. This is also very important because, like, for example, like Netflix, they run experiments on like n members, and they want to see how their n members are performing over time. So these are obviously areas that we also want to solve. Lastly, when there are covariates, we can also use this variance reduction technique, which we call the proxy outcomes. It's basically you can create any machine learning algorithm you want, just much like the W-robust estimator, and use a prediction to sort of make your variance lower. Great. So with that, I'm just going to end with an example. The example here, I think we can just think concretely. Imagine you're like a Netflix customer, and they want to decide whether or not sending a message to you is important. So whether it will increase your engagement. So in this simulation study, again, it's not super important, but here I just want to emphasize that your next response here is basically a function of it's also your previous response, which makes sense because if you think about my engagement on Netflix, probably highly correlated with yesterday's like my behavior. If I didn't finish a show, it's likely I'll probably engage and finish that show today. And on top of that, I also made the problem even harder by making each unit have a different treatment effect, which makes sense because the way I probably receive those messages, which I don't really care, and maybe like Yoff, the way he thinks about those messages are vastly different. So we want to make each unit have a different treatment effect, but on average, messaging is helpful to increase engagement by about 20. And I added some covariates to make the problem harder. So just the picture on the left is kind of what you would see if you applied our confidence sequence without thinking about X, just ignoring X. You can see if, for example, the analyst ran this for like 100 time steps, you could potentially reject, of course, and they'll likely reject with their favorite t-test. But with our method, you could reject even early at time equals 43, terminate the experiment, don't run it for all the way until 100, save further budget, and sort of move on. If you do account for our X's here and do the sort of nice proxy outcome method to reduce the variance, you can detect it much faster. Great, so that is all I want to share. I have some other extended works here in case you guys are interested, but thanks for listening. Great.
a couple of questions.
Francesca, please.
Super quick. How do you select the people that you're doing the experimentation, and how do you know it's representative sample?
That's a great question. So one weird caveat that I've been thinking about for this is when you think, it depends on the experiment. So if you're thinking about it for like a sign-up page, I feel like that's relatively kind of random, like who comes in at what time. It depends, of course, when you start your experiment. Because the thing is, you are going to, if the analyst only wants to terminate as soon as they see a positive effect, they're only going to terminate on the early samples, right? Like the people who just come faster. But that is something, of course, Netflix and like domain experts have to think hard about, like who are the things that are entering the experiment, you know?
Oh, they know a lot about it. I mean, they will be able to I mean, if they want to find a representative sample, they can based on the preferences, right? They have so much about a person profile.
Sure.
But not a sign-up. Sign-up page, they don't know nothing about you, right? You're signing up, right? You're not currently a customer.
Oh, signing up.
Yeah, but
yes.
member experiment.
For members
Other-
experiment, yeah.
Other ones, I think that.
So
Member experiment.
what they do is they assign everyone. So if you're a member, they'll assign you to a treatment. And when you log in, it gets all the different treatments you should be in, and that gives you the experience. So there is always the people who sort of see things are usually either the really, really engaged people who are on there 24/7, or just by chance if you log in. And no one really accounts for the fact that that sample is not fully representative.
Right.
Yeah, so in the, super interesting. In the panel data setting, do you allow the previous treatments to affect the outcome?
Oh, in this case, we can. I just, for simplicity, made it Bernoulli, but I can certainly say, like, in an actual application we did in our paper, not a simulation, the treatments were adaptive. Simply because they're not just sending treatments randomly. They want to send treatment like message.
Outcome.
Oh, the outcomes.
Yeah, so if I were a user, I've been exposed, previously.
Yeah. The outcomes can be completely adaptive because the design-based approach like fixes the outcome, so they're just like constants in terms of theory.
Right, but then what's the estimate?
It goes to the conditional estimates.
Right, which is kind of
it's a little bit iffy.
Right.
Yeah.
It goes into it's basically building off of the time series paper there, that has all those conditional estimates.
Right, okay.
Yeah.
Can you go back to like your second, the slide where you brought up your confident? You could go, I'm sorry, I can't remember exactly what I was.
You can just tell me to stop.
So actually, so here, right? So I was trying to understand first of all. So little m is something. It is
It's basically the maximum your tau hat I can take. Yeah.
Okay.
Yeah. Because we basically use like empirical, like Bernstein inequality.
Bernstein inequality. So I guess my I'm gonna you made a statement. I want to understand it slash. So you said big M, right? This is something that you're gonna set. It's this sort of like max value that your observed outcome can take. But in some sense, so I think about it as like the max over yi. That means that M has to be indexed by I or T or some way to maximize over it, and that means it's going to change as N changes. So like you can't really think. So the assumption of uniform boundedness is a little rough. I think, by the way, if you make the assumption that yi, as you do in your simulation, is like a like sub-Gaussian, you could just assume that like M is, then the maximum sub-Gaussian is, I don't know, square root of N or something like that.
Oh, absolutely, yeah.
So I think you can handle it, but I think the idea that you're going to just be uniformly bounded and like beyond just like sort of notational convenience seems a little strict to me.
Oh no, I mean, first of all, this here is not the best we can do. There are definitely, this is somewhat a more crude confidence sequence. We even have an appendix, a better one that is actually not asymptotic and exact. It still has some annoyance.
So you don't have to bound. You're saying you don't have to bound it by M. Then you're saying
no. So the M still comes in, but if we make sub-Gaussian assumptions, like for example that you suggested, there are papers out there, like especially Howard's paper, that does exactly what you're suggesting.
Oh, okay.
And they solved it for that.
Okay.
It's just like Yeah.
So okay, so then I guess what you're making the assumption of this uniform bound is just like for notational for like theoretical convenience. Then I think.
Sure, and just to show
Okay.
that we can do something exact. Technically, our main approach is really our main proposed one is really this asymptotic one, just because its performance is just much better. It has nothing to do with big M and all of that.
Okay, so this one you don't actually
Yes.
need the covariates to be bounded at all.
Yes.
Okay.
That's the asymptotic power. Yeah.
Got it.
And all of our that comes basically in our organization. This comes like section 3 or something, and the remainders of it just focus on this.
Got it. No, you made the statement that like hey, we can observe the M is bound. It's bounded by M, and we can observe what that is. And I think that is a little rough, but
no.
I think you can make assumptions about it and get like a sort of the distribution of the max, or maybe you don't even need.
I would like probably only use this if it's like binary response.
Yeah.
Yeah. By the way,
Oh yeah.
binary,
Well then then by definition you know exactly right.
So by the way, binary responses are very common in Netflix. Sure. So like this is very like they get happy.
That's a fair point. Yeah.
Okay.
So it actually works okay.
Yeah. Okay. Got it.
I think
I was just going to ask, I wasn't quite sure if you have a kind of a very, the treatment today has a lagged effect. So you're going to tend to stop, so that you would, you can stop earlier, right?
You would stop until that once that effect shows up.
What?
You would stop once that effect shows up, right?
One step.
Yeah. No, once that effect shows up. If it's like lagged, then the effect will show up at some point, right? So it's fine if the W's are, if the treatment has some like carryover effects, it's fine for that.
Yeah. No, I'm just trying to, so you have a treatment that has an effect early, but it's not sustained. People get used to it.
Yeah, so like the learning effect. So this definitely works, but you can imagine that if you have these types of dynamic effects, you could get yourself in trouble if you stopped it too early because it's going to disappear. Exactly.
No, in fact, Netflix calls this the novelty effect, where people when you first introduce a treatment to them, they get like, wow, it's a new treatment, and then they just get used to it. So like, if you see the treatment effect curve, it kind of like goes down.
Yeah.
Which we can detect, like in our confidence sequence, the bands will go like this, and then eventually go to 0. But if you're right in the sense that that is a decision Netflix has to make. So if they wanted to stop early, they will see a positive effect, like you suggested, right? But technically it would go down to 0, right? So maybe they should wait. It kind of depends on domain knowledge too, like what should they do there? Yeah.
And then what if people who, now not, the kinds of people who come in at day 1, 2, 3, 4 are changing very much. Like, some people come every day, and if they start on test on day 1.
So it's useful to think about it the other way around, which is the risk mitigation.
Yeah.
We were saying, which is, if it's causing harm, you want to stop it. And even if that harm was going to disappear after a few days, you kind of want to stop it because you've seen, a few thousand people are getting, everything's crashing for them and it's not working. So that's really like the really big application. That's why you want to really stop really early. So even if after a few weeks it will disappear, it's still worth stopping and figuring out, why is it the first time you see this, you hate it, right? So that's kind of as opposed to, if we see a positive effect on day 1, we want to go. So with that in mind, we're out of time. So thank you, everyone. Let's thank all of our